Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Met in, I guess, 1981 in IBM, worked on something that became a precursor of what is now known as parametric complexity. So then he was a champion of complexity of parallel computations in Fox stock community. Then I sort of lost sight of him, and then he reappeared, much more practical man, with a company, with the patents, and I think it's an interesting transformation. Let's see what a theorist can do in real life. Welcome.
Okay, I hope that it will not discourage too many. Okay, so what I will try to do is to go over a lot of material. I probably have more materials than time, so I'll need to cut things as I go forward, and I do encourage you to come up with questions. So the title of what I'm trying to do is this really short title, Piram on Chip, where Piram is the name of a theoretical model, and the addition on chip really reflects this transformation, because it says that, you know, here is this theoretical view of the world, and here I really know how to get it done in real hardware. The second title, I think, is much more appealing, hopefully, to the audience at Microsoft Research. And the question is, can parallel computing finally impact mainstream computing? What you see here is a bunch of graduate students who have been working with me, postdoc, several colleagues at Maryland who have been gracious enough to provide their expertise, and would like to proceed now to a summary, because I know that some of the Microsoft people are really busy, so I would like to drive here the take-home message that I hope will be a teaser for some of you who are not very close to the field. So I've seen in the last few months, actually even as late as this morning, some abstracts by Microsoft people, and it's clear that it has been recognized widely in this building that the fact that hardware vendors have been driving the clock speeds is becoming a matter of the past. I mean, it has been great, it has been a great ride, but it's not going to last for long. And maybe we have reached the end of it, or we are near the very end. And it has also been widely recognized that in the future, we'll have to sweat for parallelism in one way or the other. And I include concurrency in it. And there was a particular Microsoft person who even anticipated that this will be the biggest revolution in software development in the near future. I will quote him by name later. Yet to be recognized. I think that the following recognition is not yet here, and I will try as my primary objective to advance to that. So let me limit the attention for now to what's called single task completion time as a measure of performance. As you know, in computers, sometimes you are interested also in pushing as many tasks as possible within a given time. This is considered throughput. This is a very important measure, but I'm going to focus on another one, which is how to get a single task faster. So, as many of you know, between 10 and 30 years ago, some of the most talented graduate students of that time went to parallel computing to actually improve single task completion time by way of parallelism. I think the following is an adequate summary of what happened. No clear success story to build on. I think that's a proper reflection. of what happened. And actually, many of the talented people have moved on to other things, including even within this building, meaning they are not necessarily doing what they did when they worked on that. Now, where does this take us? I think that there is a big challenge here to Microsoft, as I see it. I think that there is an opportunity here, really, to change the world again, as Microsoft has done in the past, by doing it right this time. And I'm talking doing right the parallel programming thing, something that Microsoft was not a participant in the past. The other opportunity, as I see it, and I put it here very bluntly, is mess it up again and let the bottom line bleed in the parallel programmability minefield that we have experienced, like everybody that tried before. So I think that overall, people who entered this minefield were pretty wounded at the end. And I think that it's really a challenge to avoid repeating past mistakes here. I will try to present here a strategy and a methodology how to do that. And I wanted also to note that doing the same, yet repeating a different outcome is not a good idea in general. And I think that's what I would like to argue, that we certainly would prefer not to do that again. And what I wish to see, and this will be a very bombastic, high-level objective for this talk, is to see Microsoft rise to the challenge. And I don't care if they do, if Microsoft does it, not because of this talk, just because they think that that's the right thing to do. Anyway, so with this very ambitious statement, let me now go into some details and tell you a bit about my level of, my style of interest in the problem at hand and define the problem. So here is a strategic question and what it implied. So since 1979, I've devoted a majority of my time to the following strategic objective. Seek to improve general purpose single task completion time by way of parallelism. And my underlying assumption was that someday parallel computing will affect mainstream computing. Now, this was not even clear that the timing for that was not clear. And as you know, the inability to push the clock anymore is pretty recent news. So I myself was pleasantly surprised by the timing, but I think the timing is here now for this to move on. And I always, when I thought about this issue, I felt that this is a very significant strategic question, because in order to incorporate parallel programming and parallelism into computer systems, the question is, how do you go about it? What do you do first? You really need to go and refresh the whole field. And as many of you know, in the 70s and 80s, there was a tremendous amount of interest in parallel computing. And the pragmatists during those years favored the following approach. Okay, we have all this hardware, which was at that time in the form of putting many chips to work together. And the question is what to do with it. So the pragmatic thing, let's build. And once built, figure out how to best program or compile for the architectures. And the basic underlying belief of this big majority of people involved in the field was that an algorithm is worthwhile only if it fits a real machine. I came and I've always represented a minority opinion here, and that minority opinion felt very differently about it. I came with degrees, first in mathematics, only my PhD was in computer science. So I tended to appreciate the difficulty of thinking about programming, much before you even start to write your first line of code, as done by the discrete algorithms community or the academic algorithms communities and the guy who actually teach the courses on algorithms in the undergraduate curriculum. And it was clear to me that parallelism, at least in part, must come from the programmer, and it must be as simple as possible. It was also clear to me that there was nothing to build on when I joined the field in '79, meaning parallel algorithmic thinking is an alien culture. There is nothing to build on out there, and it should be understood first, meaning there is nothing to rush about building a machine before you figure out how you will have to think about it algorithmically. I felt that only once this developed, it would be appropriate to derive architecture specs and build an architecture. I admit that this was counterintuitive to many, and there was this, and if I were to summarize the difference of opinion between the two approaches, one says, which I believed in, is that parallel algorithms should be prescriptive, meaning once you understand how to think, because humans are not going to become superhumans in the next few years, they are going to have more or less the same capabilities. Once you figure that out, you derive the specs for the architecture. The other approach was prescriptive, meaning here is a machine, now go and break your head on how to use it. And the fact of the matter is that in this equation of cost, development time of software is probably the single most expensive component. So it didn't make sense to me at least that the algorithmic model should be an afterthought to fit an architecture, but rather the other way around. During the 80s mostly, there was a very significant, mostly theory community that developed the so-called pyramid theory. Many of the participants on that were theorists who just enjoyed the theory. I'm not sure that they were very much committed to one school of thought or the other. The Pyramid-on-Chip chapter that I'm about to tell you about is the current, let's call it post-theory chapter of this adventure. The goal of this talk is to describe the Pyramid-on-Chip framework that extends all the way from high-level application programmer interfaces to VLSI implementation. So it's a very broad framework that spans across many academic communities. And the emphasis of the presentation, perhaps counter to some talks which are a bit more specific, is to emphasize the what and the why more than the how. So let me define what I mean by that. The what would be what the computer system should be engineered for. In what ways, languages, will the computer system be programmed, or the specs for the system. Let me point out that from 30,000 feet, engineering, and it doesn't matter if we are talking about mechanical engineering or electrical engineering or whatever, or civil engineering, works like that. The first step is you come up with the specs of what you want to build, and only then you go and design and actually do that. I claim that in mainstream computer engineering, people didn't bother to do that for good reason, in fact, not because they were incompetent, I never say that. But what were the specs for the Pentium 4? Same as for Pentium 3, so you really didn't have to think about it. It was not an issue, but it is an issue in general, and here if we are to look into different systems, you must think about the specs before you actually do the design. The why, so of course we have to bring into the picture applications, runtime, and development time. So I'll try to review these issues. And the last thing, where, if I were to choose between the three, the last thing, if I get you sufficiently interested about the first two, you probably will have the interest to go and read about the third. I'm not sure about the opposite order. So if time will permit, I will talk a bit more about the how. OK. the following is some background on the field. So at the moment, there is the following interesting project that I take part in. It's part of the DARPA High Productivity Computer System Development Time Study. And the following is a tribal law that was formulated by several parallel programming professors who teach currently courses on parallel programming about the field. So while I believe in what is said here, it's certainly not something that I formulated. My colleagues have done that, and I'm sort of pleased to report that. So they say the following: parallel algorithms and programming for parallelism is actually easy. My claim, in parentheses, is that it's actually quite non-trivial to figure that out. You really need to work in the field like these colleagues for several years. And there is some oxymoron here, because on one hand, you need to learn much to understand how easy they are, but then it's an oxymoron how easy can be non-trivial. But that's the reality here. However, let me continue now with the tribal law, is that coarse-graining this parallelism to optimize performance on multi-chip, multi-processing with a high coordination overhead is hard. And that's really the summary of why parallel computing has not been such a success. On one hand, it looks tempting. Finding the parallelism is not difficult, but when you try to bring it down to performance, then you run into trouble. Please.
What do you mean when you say finding the parallelism is not difficult?
So I will actually give later one example of the PIRA model, and with your permission, let's defer that to that example, and then if you'll have a question, I'll take it at that point. But please remind me when I give this example, okay? So it will be an algorithm. The point is just of presenting those operations that can be done in parallel. Just that, without saying who does what or anything of that type, any serious programming effort. Okay, other side of the same coin. Decomposition first, which is the current methodology for all parallel systems, is called the composition first parallel programming approach, and this is known to be hard. And let me just remind you the term that I think was coined by Ken Kennedy of Rice University, who is a well-known figure in the field, the parallel software crisis. And this parallel software crisis is still valid. What it reflects is the reality of having these huge parallel machines, but actually relatively little software to use them. Okay. Let me further to drive a point of how relevant how things are in real practice. Let me quote a press release from Intel from 2 weeks ago. They wrote the following: the game is over for software that is written only for a single processor. Intel is providing the platform and tools to help out the game developers as they start the transition to a multi-core and multi-thread environment. Now, I think that this quote first tells you where Intel puts its effort now, and second, it raises a question. Will we be able to program these hardware-centric architectures? Are we running into the same difficulties again? I believe that the latter is true. But you see here really fundamentally the same collision between two different schools of thought. The one that tells you, here's the architecture, go and figure out how to program it, and the other that tells you, you must first figure that out and then build. So I think that what you see here is really an importation or a reincarnation of the story of parallel computing happening at mainstream computing, which I think is really exciting. Okay. Here are a few comments about the PIRAM model. And the PIRAM is an acronym for Parallel Random Access Model or machine. When you say machine, you really mean virtual machine. You don't really mean hardware. So in the ideal PIRAM, you make the unrealistic assumption that latency for arbitrary number of memory accesses is the same as one access. So that's the essence of the Piram. The other assumption here is that when it comes to performance, the algorithmicist states, or at least doesn't hide, what can be done concurrently. An algorithmic knowledge base, which is second in its magnitude only to serial algorithms, was developed. It is by far the simplest parallel model for algorithms, and quite a few surveys and whole books have been written and devoted to this topic. Since some time has passed since this knowledge base got all the attention, let me do some computer science archaeology here and tell you a few facts about the presence of knowledge in this theory, So during the time frame of 1988 to 1990, some of the most important, mostly used algorithm textbooks have chosen to include a major chapter on Piram algorithms. For some of you who know these texts, they know that these were the most heavily used during these times. Maybe there was another one in this list, but it made it. So this was the model of choice for parallel algorithms in all major algorithms theory communities. It was taught everywhere. Furthermore, during the 70s until the early 90s, there was a fierce battle of ideas by a lot of computer science talent who were looking for the ultimate parallel programming model that will allow both easy expression of parallel algorithms and their programs, and the validation of the model by algorithmic paradigm and solutions for as many problems as possible. The Piram approach has emerged as a clear winner. So to the extent that there is some Darwinistic choice taking place, this has happened. So it's very important to take this into account. There was a serious competition there, and there was a clear winner. So Darwin has spoken, I claim. Now, the following is a hypothetical statement. Suppose one could build, in 1990, a computer that could support Piram-like programming. The premise is that Piram algorithms would be studied now by every undergraduate computer scientist everywhere. And the fact is that it made it already into textbooks. It was there. There was a serious problem with implementation that I'm going to mention and review later. Okay? Now I'm going to address your question about expressing simple parallelism. So in order to make this presentation of the Piram more tangible, to those of you who are not familiar with this theory, and let me tell you that it takes me the better part of the semester to teach this theory, but I'm going to give you here in 5 minutes the essence of how an algorithm looks there. Consider the book of flights, meaning you are given all the commercial airports in the world. And for each airport, for each of them, you are given all the non-stop flights from them to any other airport. What I want you to find or to compute is the smallest number of flights from your favorite airport, say Washington Reagan, for me, to every other airport. So I hope that the problem definition is clear, and I hope that by now everybody who remembers still what they studied when they were undergraduate, you figure out that the textbook algorithm for this problem is BreadthFirst Search. Now, let me surprise you. The Piram algorithm will be exactly that, okay? Which is easy enough, right? Because you're already familiar with it. So how does the Piram algorithm look? It's an inductive algorithm where in step I, you already are given all the airports which require I-1 flights to them. And now you explore from them and concurrently find all those that require I flights. So for instance, if you need 3 flights from Washington Reagan to Delhi, you find all those that require 2 flights, and now the flights, say, from Zurich, Rome, London, Paris, will all potentially tell Delhi you are 3 away from Washington Reagan. The statement that you do it concurrently, this exploration per layer of the algorithm, is the only change relative to the serial algorithm. To remind you, in the serial algorithm, instead of doing it concurrently, that's the way maybe you phrase the algorithm originally, but then when you teach students to program it, you impose a queue order, first in, first out. And by the time you write your code, not even the smartest compiler person will be able to undo the damage and extract the parallelism that you saw before. Okay, so as far as I'm concerned, this is the answer to your question. You see, the fact that as you advance from one layer to the other, you see all the parallelism. So when I say parallelism is easy, this type of parallelism is easy. Okay. Now, what I want you to observe is, first, the difference relative to the serial one. The second thing is that if you are to take this algorithm and program it on a multi-chip organization where you must do the composition first, you will be messed up with this algorithm. How do you do the composition? It's not clear. It all depends on the pointers and how you get there. So, please.
I'm lost with your definition of composition or decomposition.
Okay. So the composition is the need to take the computational task at hand at each point as you advance, and you need to break it into big computational pieces, assign each to a different processor, and only then communicate again. So the composition first is a name I've given to this methodology that is used now for parallel programming.
So it's the necessity of dealing only with coarse-grained parallelism.
Exactly. Coarse-grained is exactly the term. That's exactly what it's exactly a synonym for what I'm trying to say. Very good. Okay. So let's look at the performance picture. The inherent serialization of the parallel algorithm will be the number of parallel steps. So if the furthest city in the world, the furthest airport in the world from Washington Reagan requires 5 or 6 flights, and if you think about it, you'll probably see that that's correct, then the number of steps of the parallel algorithm will be 5 or 6. What is the total number of operations of this algorithm? So if you open the book of flights, you will see that you have in excess of 400,000 flights a day. So this will be the total number of operations. But for the serial algorithm, this will be actually the number of steps. Now, of course, it's not completely fair to compare 6 steps to 400,000 because it's completely unreasonable to expect that you will be able to implement each of these steps at the same time as each of the 400,000. But even if it will take you 100 clocks or 1,000 clocks to implement each of the steps, you are still way ahead with the parallel algorithm. So there is a decisive advantage relative to coarse-grained parallelism. The next observation I wanted to share with you is that this was a particularly simple example to teach the basic methods of the Piram approach. And to reach the conclusion that parallelism is easy, you need to take the better part of a semester in a course on this topic. I guess this actually creates or sheds some light on the political problem of advancing this approach in Washington or in the VC market or wherever you would like to do it. Because the expectation in Washington when you go to DARPA is that they would like your explanation to be solid and quick. Okay, so solid I accept. But quick, how can you do it in a quick way where what your basic argument is more like relying on a calculus-like knowledge? And as we all know about calculus, once you master it, it's very easy. But it takes a while to figure out what's going on there. So if I were to build something based on calculus and you don't know anything about it, it's not easy to convince you in 5 minutes that this will fly. And there is some sense of that in this parallel algorithmic theory. Once, when Albert Einstein was approached by the Washington types of the first half of the century to explain very quickly what he does, he lost his patience and came up with the following statement. It's okay to do your best to make everything as simple as possible, but not simpler than that. Okay. So I think there is an issue here of how quickly you can explain the essence of this approach, and I don't have a good solution for that, frankly. I can only rely on the impression of everybody who has been doing that. Okay, in reality, only multi-chip, multi-processors were available. So what were the options that we faced in the 90s? Run as is. Take the PRAM, run it as is. You ran into significant problems with performance. Overheads were too high. And the reason, just to summarize it, was that when you have multi-chips and you need to move data between them, the bandwidth was insufficient. So, in particular, the paper that came out of University of California at Berkeley, the log-P paper in 1993, which was very well cited, branded the PRAM as unrealistic and said it shouldn't be taught. The outcome was that, with the exception of a few, including me, I'm not sure there are too many in this group, the PRAM non-complexity community really dispersed. Funding dried up. Later versions of a key textbook chose to take the PRAM chapter out. And the fact of natural selection didn't really register, which I think is very significant. I've actually tried this argument on Computer Architect, and they were really impressed by this argument. They just didn't know it. So what was the other option in the 90s? To tune for a machine. So this dictated the composition first parallel programming, very high development time cost. How successful? I'll let you be the judge. I can tell you that I tried to Google in order to figure out how many parallel programming classes are offered in spring 2005 in North America. I found rather few. So there was a real tragedy there, if you will. What was buildable was not programmable. What was programmable was not buildable. So this is where we ended up in the mid-90s, into today. The new DARPA term is actually look at productivity. I think that's also quite important, where you look also at development time. So this was a way for DARPA to incorporate the difficulty in programming into its current generation of funding in this field. What happened to mainstream computing? Reliance was on serial code. The maximum issue per clock, meaning how many instructions you can start in a clock, for successfully commercial processors working on a single task was in 12 years ago, say, well, the range was between 2 and 6. What's the range now? Between 3 and 4. So this is completely flat. So you have stagnations there, and we also know that faster clocks are not what they used to be. I mean, please.
These 3 and 4 look very theoretical. I think in most real apps it's less than 1.
No, I said maximum issue.
Right. And
yeah. Oh, yeah, right.
Irrelevant.
Oh, yeah. I completely agree with you. And let me turn around and actually phrase it in a different way. The reason that you have 3 and 4 is because I want to accommodate those rare cases where you can get it. Because if the average was 3 and 4, what you would have seen here was probably 10 to 20. So you are exactly right. Yeah. So Gideon's point is well taken. I completely agree with this statement. So in fact, the average is well below that. This is the maximum. And in fact, the way to interpret the 2 to 6 is that 12 years ago, give or take, it was an open issue. So the 6 were the optimists and the 2 were the pessimists. When you see 3 to 4, you see convergence. Anyway, thanks for your comment. So the quantitative hardware enabler, which is the good news, is that if you look at 1980, the Intel 8086 processor, which was in the first IBM PC, had 29,000 transistors. Now you can put 1 billion, which is a factor of 30,000, very significant enabler. So how can we put this quantity advantage to good use? So the main new insight, which allows me to go back and say that the reservation made in the log P paper is not relevant anymore, is that the low overheads are possible with on-chip multiprocessors. So if you put now the processors on a single chip, and you have the budget to put even 1,000 of them on a single chip, the bandwidth is not a killer as it used to be, because on chip you can have 2 orders of magnitude better bandwidth than if you have to rely on pins connecting chips together. So this was a key insight. The PRAM on chip relies on the ability to get much better bandwidths and better latencies when you operate on chip. This means that option 1, and just to remind you, option 1 was run as is PRAM-like code, is alive again. And the question is, why not to roll back to this time period when there was this tremendous momentum and just teach the PRAM chapter? So I claim that, in fact, the case has become much stronger than it was at that point in time. I claim that the case now is orders of magnitude stronger because of things I'm going to tell you. So not only that there was a clear Darwinistic choice, the case has become much stronger. So please bear with me and see this, these new observations about this case. The productivity picture. So productivity means cost of programming, not only runtime. So the productivity picture breaks into two to a first approximation, into more refined partitioning if you take a closer look. On one hand, you have the performance programmer, the guy who will spend all the time possible to get the best performance. And on the other, you have the high-level API enabler. Let me explain that. The idea is to have an API such as MATLAB or OpenGL or some game developer APIs that do not require a degree in computer science to program. And the question is, can you come up with the following win-win proposition? That give me your favorite application, come up with an API where programming is way easier than C programming, on one hand, up to a point where a non-computer scientist, just an application expert, can do that. And best, it can be just even an existing API, as the ones I mentioned. And the other thing that will make it a win-win proposition, not only that it will be so much easier to develop the code, you will actually be able to extract parallelism from it, and you will end up with performance which will be better than the C code that you have to work so hard to produce, because it will be done on a higher level API. So this is really hard to beat. Better performance and easier, cheaper to develop.
So in the second case, the programmer will be writing essentially serial code. The libraries would turn it into parallel operations.
No, I claim that it's not. You may, if you want to think about it serial, I have no problem. But I claim that some of the statements in MATLAB or VHDL or Verilog or OpenGL, you call it serial, but in fact, it's not as serial as C programming. C programming is serial to the bone.
Yes.
So as far as I'm concerned, this application programmer interfaces, I would like to call them more application APIs as opposed to serial programming. Because the story of failure of extracting parallelism from, by compiler from serial C code, I don't think is relevant here. Because here you have a lot of parallelism you can extract from these APIs. And this is the prototyping that two of the people working with me are prototyping now. One Olano, who is a professor at UMBC, University of Maryland, Baltimore County, works on prototyping OpenGL, and I have a current master student who is prototyping VHDL. Okay, so if you want to call it serial, that's fine. But the point is that it's not as serial as the C interface. Okay. So in some sense, it's almost too good to be true because it's really a win-win. Now, we also need to recall that there was a limited success to relying on compilers to extract code from serial C code. And by going to APIs, we detour this historical difficulty. And in my mind, in the geopolitics of parallel computing, this is the third and perhaps the most significant change that has happened in the last 3 years. So what are the big changes? Let's count them. One change is that you have enough hardware to put on a single chip. This was not possible 15 years ago. The second thing is that Intel and other vendors do not know to push the clock. Major change. And the third change is that you have APIs which have succeeded and emerged, and you can extract from them parallelism by compiler. I mean, these three things created a completely new terrain, which was not there when people really considered this seriously 12 to 15 years ago. Please.
Just to make sure I understand, it might be similar to your question. So basically, this approach is to hide the parallelism inside libraries.
Yeah.
And the libraries might be domain-specific, like some of these, or they might be more general, like OpenMP.
Yes.
Okay.
Yeah, libraries is a good keyword to note here. I accept. Yeah.
But also, writing the libraries is an awful lot harder than you're saying.
Of course, yeah. So if you ask, so let's look at people by competence. So if we are to look at these computer science graduates, who really know to write performance programming, they will, if you have such an API, you as an application programmer will still drive the same car, but you need a real expert to replace the engine under the hood in order to do it. So there is no, I don't know to avoid that.
Oh, of course.
Yeah, but it's important to, I appreciate your question because it really articulates the issue. Let me just redraw what I said now in two figures. So in this figure, I look at the performance programming domain. So what you see here is in the leftmost branch here, you see the current reality. So in performance programming, what's going on? You come with a basic algorithm, which is a somewhat informal concept. Then, what do you do with it? You add some data structures. In order to make it a serial algorithm, you write code in C, and you run it on available serial machine. What is the current multi-chip, multi-processing alternative? Do the same here, but now do the composition or the coarse graining, as you called it, and do all these things, assignment, orchestration, mapping. I mean, this recipe is taken from this book, which is the leading textbook now on parallel programming by Dave Kaller and Singh. And finally, run it on a parallel computer. What I propose on an XMT-like, the Pyramon chip platform, is to add parallel data structures, much as was done in the example of BreadthFirst Search. Rather than a queue, do something else. Then program it in an extension of C, which I call XMTC. XMT is the name of the platform for explicit multithreading. Then just run it here with low overheads on the architecture, which at the present time is a simulator. The claim is that 4, which is what I advocate, is significantly easier than 2. And in fact, it's competitive with 1. It's the same process. And the current DARPA project, High Productivity Computer System, in fact puts it to a test. And just to tell you what is being done now, and my graduate course at Maryland participates in this experiment, DARPA is funding about 7 classes at Maryland, MIT, University of Southern California, San Diego, Santa Barbara, and USC, and several others. And they try to follow the learning curve of students when they are exposed to parallel programming. And they try to compare it to serial programming and between them. So my claim that this is competitive is actually being now put to the test. And I actually, as we speak, my students work on homework 3 in this class and actually tried it. So this is actually something which is a funded effort that is conducted by software engineering experts whose expertise is really to look over the shoulder of programmers and figure out how difficult it is for them to learn and do the job. How will the application programming look like? So we'll have an application programmer interface, which will be perhaps a standard interface like OpenGL, VHDL, Verilog, MATLAB. Using compiler, you will be able either to translate it as is done now into serial program and run on a standard computer, and this will be automatic, or take it in this direction because there will be a lot of parallelism that you will be able to express here. But it is not at all clear that in many cases you can actually automatically translate it here because of the coarse graining challenge, the decomposition first. Okay?
You come across the work by Pete Tuttle 30 years ago on the 7600, where he did something similar? No. Okay. He figured out you can build a vectorized API and get like 2.5 times the speed of the best compiler.
Yeah, I'll tell you, just to be completely fair here, this viewpoint that you see here, I'm far from claiming originality on it. Okay? This actually is a joint vision which emerges as an underlying vision for this DARPA project. So if I gave you the impression that I think that I'm inventing here something that nobody has ever thought about, I don't believe it, okay? Myself. Okay, so but the point is that this motivation and this matter of fact, I mean, what was not there in the 70s was the fact that these APIs made it. Okay, but by all means, I'll be glad to recognize this work. But I'm really trying to recap here a recognition that emerged in this community that DARPA put together. Please.
I'm trying to think about like where Google's MapReduce kind of approach would fit into this, or is it just another angle at it, you know? Or is it addressing a different problem?
I'm not familiar exactly with that. What is?
They call it MapReduce. It's a so Google's research group, and in fact even I think their product kind of thing, just runs on a whole lot of machines.
Okay.
And MapReduce it's kind of like old thinking machines kinds of approaches, where you just have this vector you can think about spread across machines and do the same calculation everywhere, and like a parallel scan or something. But it's worth thinking. Maybe you can look it up. It's easy.
I'll tell you, in some way, this may be an orthogonal issue because I'm talking about a single task, and in some cases, to be completely fair, you can harness the current parallel computers for that, and Google has done a good job in that.
But a lot of tasks are just embarrassingly parallel.
I agree, and in that case, my increment is not as significant. So I'm far from arguing that parallel computing has been a complete flop. I'm not saying that. I'm saying if we are to learn from the lessons for parallel computing and try to import them into mainstream computing, we should learn from the success stories and the failure stories of parallel computing. Because clearly, some things, embarrassingly parallel, are done very nicely there. But some things have not succeeded. So I'm trying to really maybe I'm highlighting more the problematic side than the success side, but I think that in fairness, the picture is more complex than just success or failure. It's a mixed picture. So Google and quite a few other applications, if you see what some people are doing with this huge machine, some are putting it to good use. It's not a complete failure, far from that. But it is not the same success story. Like, if you are trying today to take the most performance-demanding components in Microsoft products and try to run them on these parallel machines, I doubt whether they will work well in game development applications and others. So, that's the level of my comment. But anyway, the point is that this viewpoint, I think, is clearly, to many computer scientists, I think it's a clear ideal that we would like to get. So for many years, people wondered what will happen with this parallel computing thing. People said serial computing will reach an end. You will not be able to do it faster. And you heard it in the early 70s. And you could have responded to that in two ways. One is that this opportunity will run forever, or you can respond to it in the same way that Mark Twain responded to the news in a newspaper one day that he died. So he didn't say it's completely incorrect. He said it was premature. Okay, so the news in the 70s that serial computing is reaching an end, it was not really wrong. It was just premature. And in 2005, it's finally becoming a reality. So the XMT or pyramid chip vision was introduced in 97, and I can tell you that I feel that the world is getting significantly closer. As you may know, Sun is coming out with 32 CPUs on a chip. Intel announced that all their future processor chips will have multiple CPUs. Herb Sutter of Microsoft just published an article entitled "The Free Lunch is Over," a fundamental turn towards concurrency in software. And that's the fellow I quoted before. And he believes that the fundamental turn that this puts software development in is comparable, if not more significant, than the introduction of object-oriented programming, which is his territory at Microsoft. So I think this is a pretty impressive statement coming from him. Burton Smith, the chief scientist of Cray, said in an interview last November that parallelism to date has been a nice strategy for HPC users, but an afterthought for everybody else. And he makes here a specific reference to Microsoft. If Microsoft wanted to write Office in a parallel language, what would that language be? What would be the architecture to support it? We don't have a good answer to that. I believe that the XMT approach provides an answer to this question. These type of questions. So the question is, how will things emerge? Will it happen the hard way, where you will have more processors per chip, more threads, and so on, and then at some point software companies such as Microsoft will say, we cannot take it anymore, we need to switch? Or can it be done in a more strategic way, where people will look in the future and get ready for that? I, of course, advocate the second. And let me just tell you that there is an interesting recognition coming out from Europe. There is a consortium of 5 companies, pretty big companies, and 10 top universities in Europe that submits actually today a big proposal at almost $10 million for the first 18 months in order to actually implement this PRAM-on-chip vision in Europe. So I was quite pleased to see that there is this tremendous following there. I wish I could have said the same about the activity on this side of the Atlantic. Some application domains. So you perhaps know the list as well as I do, at least some of the people in this room, but let me mention a few applications. Interactive visualization, virtual reality, computer-aided design, control of switch fabric, ballistic missile defense, weather forecasting, radar processing, weapon design. There is one particular application which I think is particularly exciting if you want to simulate a biological system where you have these interactions at the clock of nature, so to speak, where you need to emulate quantum effects where the clock ticks at 10 to the minus 14 of a second. If you would like to do it for, say, a second, you have 10 to the 14 steps. So you really need a very fast system and do all the parallelism together. And if you want to do it on a multi-chip organization, where just the round trip communication for communication purposes, just to do some synchronization takes a microsecond, you have 10 to the 14 times 10 to the minus 6, which is 10 to the 8 seconds, which is more than 1,000 days. However, if you do 10 to the 14 times 10 to the minus 9, it's 100,000 seconds, which is just a day and a quarter, which is more likely to be within reach. Okay. I really have limited time left, so I'm now reaching a point where I can tell you a bit about the architecture, and I wonder what would be the best strategy here. So the main point is that the PRAM gives algorithm scalability. In hardware, what can you do? You can put more of the same, and you can put strong interconnects. How do you translate this into that? So that's the big effort here, which is called explicit multithreading, which is a framework extending from applications to implementation. And the idea is to create a strategic design point that will replace the 1946 design point by von Neumann. The question is, how much time do I have? Because I can go and point out some main components. Do I have any?
Not much, but finish.
I'm sorry?
You finish in a couple of minutes.
Okay. Okay. So let's see what I can do within this time limit.
You lose your audience.
I'm sorry?
You may lose your audience.
Yeah, no, I think I probably already enough of your attention span here. So let me just tell you about one structure and leave you with that, which was really the second patent in what I submitted on this technology. So, and this will be probably my last slide. So consider the following a machine extension to the von Neumann model, okay? So, you know, one of the things that explained in the encyclopedia, how does a computer work, is this control structure composed of a program counter and a stored program. And this has been a remarkable success story because it was documented in 1946, and now that the clock is 100,000 times faster, still the same control structure is used. A very boring area, right? I mean, same paradigm. So since it managed to survive this tremendous improvement, I think it can be classified as a remarkable Darwinistic success story. And it will be more pragmatic to upgrade it rather than replace it. So my suggestion would be to try and re-axiomatize the von Neumann mathematical machine in a way that will provide also backward software compatibility. So one of my personal stories is that because I moved from math to computer science only after getting my master's in math, it was not clear to me how computers really work. And contrary to some teenagers who now hear about the program counter and stored program when they are 14, I heard it probably when I was 26 or something like that. So I could appreciate the insight. So how does it work? Let me remind you. This is what everybody knows. You have here a stored program. You bring one command at a time to a program counter. The program counter looks at the left side of the command, which tells it what to do. The right side tells it what to bring next. Okay? Typically, it's the next command. Sometimes it's a branch or a jump. Then you have to jump here. How do we as programmers think about it? Here we have the book of commands. Now we have our finger. And our finger advances from line to line in the book of commands. And the only difference between this picture and this picture is that while here the finger was idle and the information was brought to it, here the finger moves. But the duality between these two is so trivial that nobody actually bothers to even point that there is a theorem or an observation here, because it's so straightforward. Now, what I will try to do here is to magnify this duality and actually argue that there is merit in looking at this point and creating a new duality which will be more powerful for parallelism. So how will things look from the parallel programming point of view? And this is something that I really had to skip because I didn't have time to tell you about the how too much. So we will have serial mode here, where the program counter will work by reading just a serial program. Then it will hit a spawn command. And the spawn command may tell it, spawn as many threads as you will. You want 1 million, put 1 million there. Whatever you dream up, everything is fine, because that's a virtual thing. Now, you have here one, say, page in memory that is to be read by these 1 million threads. And the mode of programming is what's called single program multiple data. Now, each of these programs read this page with a different ID. Please.
Is it the same as SIMD, single instruction multiple data?
No. SPMD is more relaxed. SIMD is where soldiers are marching. SPMD, it's the same program, but you can advance through the program at your own speed, take different branches. So it's more relaxed. It's more, SIMD is a hardware concept. SPMD is a software concept that was introduced in IBM in the 80s, by the way.
So you're executing the same routine against different data?
Yeah, so the point is that each thread will have its own ID. So if you will have a command like copy $, to B $. So if you are thread number 5, for you $, will mean A5. If you are thread number 6, it will mean A6. So the commands, the only difference will be the reference to an ID. And again, I apologize. There was so much I could do in this talk, so I'll be glad to tell you more about it, but I just don't think it's fair to hold the whole audience for that. But so this is the mode of programming. And then each thread will hit a join command, and when they all hit it, they go back to serial mode. How will this look on the hardware side? The big difference on the hardware side is that on the hardware side, you cannot dream any number you want. The number of processors must be fixed. So suppose you have 1,000 of them. So the serial piece of code will be identical. You just have this program counter match this one. But when you move to parallel code, what will happen here is that upon reaching a spawn, you broadcast the code to all the hardware contexts. Suppose you have 1,000 of them. And you start executing the first 1,000 out of the 1 million. The point is that the broadcasting is very efficient because the program is the same, but it's going to be interpreted differently because everyone will have a different ID. So if you have $, you interpret it differently. And then the next question is, how do you emulate the whole 1 million by this 1,000? And the answer to that is the following. I need to show you here the control side of things. So you are given a spawn of 1 million threads. How will the hardware determine who does what? So you start by naive assignment here, where thread control unit number 5 executes virtual thread number 5. And you also broadcast the number n, million, to everybody. And you ask, is the next thread control unit, virtual thread I'm to execute, is it larger than the scope? If yes, you finish. If not, you execute. And then you go here to another patent I have, which is really an implementation of the famous fetch and adder, fetch and increment construct that came out of NYU in the early 80s. And from that, you plug in your interest, and you get back a new number which is guaranteed to be different than anybody else. Then you check whether you exceeded the scope. If yes, you finish. If not, you execute, and you call again. So this shows you that the only place in which all these units communicate in the control structure is by communicate through this hardwired fetch and add unit. Okay, so this gives you a feeling, I hope, of how you emulate these 1,000 threads by local control, this million virtual threads by local control of 1,000. Okay, so yeah, let me just advance to the conclusion slides here. Objectives, general purpose computing, single task completion time. In the past, the predicaments were high overheads for managing parallelism in multi-chip, multiprocessor. They dictated the composition-first parallel programming. In the past, there were also good returns on using on-chip growth for caches, now diminishing. Architecture techniques have been mined out. I claim that the approach is new yet conservative. We demonstrated speed-ups in the range of 50 to 100, productivity picture, and so on. So I think that with that, I'm probably finished. Maybe let me just throw in one last comment which applies to the Microsoft environment. There is the following catch-22 situation when it comes to the Wintel platform, Windows plus Intel. Intel asks who will develop the operating system and the software development kits APIs. Microsoft asks who will build. The result is that the obvious is done, no planning, and no action actually hurts the whole field. And I think that what is really needed is a prototype study where I hope Microsoft could initiate, showing that if something will be provided, then it will be great. Then it will be a no-brainer to go and build it. So that's the reason actually for coming up.
So you think the first step should be done by Microsoft?
I believe so, yeah. I believe so. It may be counterintuitive, but I believe so.
Yes, thank you. Yes. More questions?
I had a question going back to the slides you were just showing with about spawning the PC counters. So in that model, is every processor connected to the same memory? Is there one memory bank?
Okay, data memory was completely abstracted in that discussion. It's a big topic. I mean, I hope it was clear to you that, that I have probably something like 12 slides. Out of them I presented 2. I'll be glad to discuss it, but clearly in this discussion, only control, only program, the instruction memory was touched upon in the control, no data memory. I mean, that's a big topic.
You can say that because you will stay the rest of the day here. So if you don't meet,
I'll be glad to talk to you in person about that.
Last example that you were giving, it felt a lot like parallel for loops in OpenMP, for example. Is that just an artifact of the example, or is this something more general?
Which example are you talking about?
Parallel for loops in libraries like OpenMP?
No, but which example in my talk?
The one with the multiple program counters and spawning and multiple threads and then merging together.
This was really an implementation of hardware. I hope that it was clear that I'm talking about taking the hardwired stored program and program counter and extend them. So this was not a language comment, it was a hardware comment, really hardware design. Now, the connection to OpenMP, I have no objection to OpenMP. I would like to support it, but at the same time, I think that OpenMP is a bit too limited because it's engineered for the current generation of multiprocessors.
Sure.
So the OpenMP is a great concept, and I'm all for advancing more in this direction.
Oh, I think it's industrial strength duct tape. I mean, it's great for what it does, but we do need something more. I was just curious because it looked a lot like it. I was wondering if you were going beyond it, if you were proposing something more.
Yeah, it's much beyond that because I'm actually suggesting to give a hardwired control for the parallelism on chip. You see, it will really, what I'm proposing here is something that, if accepted, will be taught in every class to introductory computer architecture as the control structure that is the next generation after the von Neumann structure, which has not changed. So it was really a computer architecture type of
We suggest that the rest
point.
be taken offline. Thank you again.
Thank you.